Automatic Addison.
In this tutorial, we will consider the MoveIt Task Constructor for ROS 2 to carry out a pick-and-place task. Here is what you will build by the end of this tutorial. We'll use a depth camera to dynamically detect and locate objects in the scene. By the end of this tutorial, you'll have created a vision-enhanced pick-and-place system that demonstrates the power of combining perception with sophisticated motion planning. Okay, the first thing we need to do is create a package to store our code. So I'm going to go to, let's just go to the root. We go to cd ROS2, source, MyCobot ROS2. Let's create the package, ROS2 package create, -- build -- type, ment _CMake, -- dependencies, generate parameter library, lib pcl -all -dev, MoveIt _common. Remember, go slow, folks, so you don't make mistakes. MoveIt _core. MoveIt _ROS _planning. MoveIt _ROS _planning _interface. MoveIt _task _constructor _core. So got some more. MoveIt _task _constructor _msgs. PCL _conversions. PCL _ROS, RCL CPP, sensor _messages, shape _messages, TF2 _eigen, TF2 _geometry _messages, -- license, BSD, -3 -clause, maintainer, name Ubuntu, maintainer, email, automatic Addison at todo.com, and then description. Pick and place demo using the MoveIt Task Constructor for motion planning and the PointCloud library for perception. MyCobot _mtc _pick _place _demo. And press enter. Now let's go cd to the workspace. Now let's do ROS dep install -- from -paths, src -- ignore src -r -y. All required ROS deps installed successfully. Okay, everything has been installed successfully. Now, because we're going to run the build command, -build, all the time, I want to introduce you to this alias. You've probably seen it before if you've been following my tutorials. So I have the build alias, which CDs into the ROS2 workspace, runs -build, and sources the bash RC. Okay, and just to show you here, my bash RC file. My bash RC file sources the ROS2 distribution and the ROS2 workspace. So I don't like typing that command again and again and again, so I just make it an alias, okay, into build. And if you want to know how to do that, go look at my setup tutorial. But I'm going to type build right now to build everything. Okay. It barked right here about the lib PCL all dev. Don't worry about build errors for now. We will fix all of that later. Now let's clear. Now let's create some launch files. All right, let's go into CD source, CD mycobot ROS2, CD mycobot MTC pick and place. Now let's see what we got in here. Let's make a folder called launch, make dir launch. And CD launch. Okay, and let's add our first file in there. So I'm going to go down here. Let's add this. Let's go to launch. Okay, let's go to my downloads where I have cloned the repository to my GitHub. Launch. And we've got 3 files that I want to add. So the first file is going to be pickplaceDemo.launch.py. So this file is going to launch the MoveIt Task Constructor node responsible for pick and place with perception. We've got the PointCloud viewer.launch.py. This launch file is created for viewing PointCloud data, which are PCD files in RViz. Starts a node to convert PCD files to point clouds. And allows configuration of the paths and publishing intervals. It launches RViz with a specific configuration for visualizing the point cloud data. And then we've got another file right here, getPlanningSceneServer.launch.py. This one right here, just open it up real quick so you can see. This one right here will start the getPlanningSceneServer node. And we'll go over this later in more detail in this tutorial. But this is responsible for providing the current planning scene. So it loads the configuration parameters from a YAML file. So let's get all of these launch files, do a copy. Let's go over here and we'll paste. That's it. Add those launch files. Now let's install the packet capture library. You don't need to worry about what this is. Just install it. So sudo apt-get install lib pcap-dev. Type your password. Install all of that. All right. Make sure it's installed. All good. All right, now let's add some parameters. Let's go to here. To source mycobot ROS2. And let's just create a new folder here called, oh, no, not here. Need to go in the pick and place demo. Let's create a new folder here called config. This is where I'll put the parameters. Right in this right here. And let's go over here. Again, folks, you can obviously clone this to your own repository, but I like to do it piece by piece so you can understand the full workflow of how you would build this up from scratch. If you had another robotic arm, for example. So sure, you could just clone it and use it, but this is how we are going to learn. So we go step by step. Let's go to config. And we've got 2 parameter files here. Get planning scene. Okay, so let's talk about this one first, this MTC node param. Let's just open that up. So this YAML file contains configuration parameters for the MoveIt Task Constructor. Okay, it includes settings for robot control, object manipulation, motion planning, and various timeout and scaling factors. So these parameters define the behavior of the pick and place task, including grasp generation, okay, approach distances, and Cartesian motion settings. So let's just add that puppy over into our folder. And we've got one more we need to add. This guy right here, the getPlanningSceneServer.yaml. So this file sets parameters for the getPlanningSceneServer node. So it includes settings like point cloud processing, plane and object segmentation, support surface detection, and different thresholds. I'll show you here, different thresholds for filtering and clustering. So you can go through this at your own convenience. So these parameters are for processing sensor data and creating an accurate representation of the planning scene. That's what this one's for. Let's copy that. Let's go over here and paste. Okay, now let's add the source code. So let's open this. ROS2, source, MyCobalt ROS2, pick place demo, source folder. It's empty right now. Let's go over here. Downloads, .ROS2, pick place demo, and source. And we're going to add this mtc node.cpp. Let's add that over here. So let's open this puppy up. What does this file do? So this file implements the main MoveIt Task Constructor node for the pick and place task. It sets the planning scene, creates the MoveIt Task Constructor task with various stages such as move to pick, grasp, lift, and place. So the file also handles the execution of the task, coordinating the robot's movements to complete the pick and place operation. Let's close that puppy. We've got some more. Let's add the cluster extraction.cpp. What does this guy do? Open this one up. Again, I created all of these from scratch, so you can go in and have a look and get really into the weeds and understand what's going on with the algorithms and so forth. But let me explain it at a high level. So the cluster extraction.cpp file contains functions for extracting clusters from a point cloud using a region growing algorithm. So it helps in separating different objects in the scene by grouping points that likely belong to the same object. The extracted clusters can then be processed individually for object recognition or manipulation tasks. So let's close this. Now we've got the get planning scene client.cpp. Let's add this puppy. Open this. So this guy implements a test client for the get planning scene service. It's responsible for requesting the current planning scene, which includes information about objects in the environment. Let's close. All right, let's get the get planning scene server, which is the complement there to the client. Let's add that. And this guy right here, let's open it up. This file right here implements the server for the get planning scene service. So it processes PointCloud and RGB, red, green, blue image data to generate collision objects for the MoveIt planning scene. And these collision objects represent obstacles and objects in the robot's environment. And they allow for accurate motion planning and object manipulation. So close. Now we've got another one, normals, curvature, and RSD estimation. Let's put that in here. Okay, so this file, let's open it up. This file right here contains functions to estimate the normal vectors, the curvature values, and the radius base surface descriptor values for each point in a point cloud. Okay, it's a mouthful. So those features that I just mentioned, normal vectors, okay, curvature values, and radius base surface descriptor values. You'll see it in different academic literature as RSD values. So these features right here, they help in understanding the shape and orientation of the different surfaces in the scene. So the estimated features can then be used for tasks such as object recognition, segmentation, and grasp planning. Close it. Got some more. Object segmentation.cpp. Let's put that over here. Object segmentation.cpp. So this file does most of the heavy lifting. It implements object segmentation for the input 3D point cloud. It includes functions for fitting geometric primitives, so cylinders and boxes, to point cloud data, which is then used to identify and represent objects in the scene. Close that. another one. We've got plain segmentation.cpp. Let's add that. So this file right here contains functions to segment the support plane and objects from a given point cloud. So it identifies the surface on which objects are placed, okay? Think of like a table, okay? And it separates it from the objects themselves. This segmentation is important for tasks such as determining where objects are located and where objects are placed. Okay, and it's got a whole bunch of parameters and a whole bunch of stuff in here. Close it. Okay, now let's create a header file. So let's go over here. Actually, let's just open it up here. Okay, let's go to Downloads. MyCobot ROS 2, Pick and Place Demo. Include. This guy over here, we've got all of our header files. Okay, and these header files define the interfaces, okay, for the corresponding source files that I mentioned earlier. So they contain the function declarations, class definitions, and necessary include statements. So we'll just copy all of that. And we'll go over here, ROS 2. This tutorial would be 5 hours long if I went through each of these. So if you have some time, I encourage you to go through each of these to understand what's going on under the hood. Okay, it's a lot of stuff going on. All right. So now we've got the header files in place. Now it's time to add the launch scripts. Let's go over here to the repo. Got our scripts. Okay, let's go over here to our actual workspace. I'm going to go into MyCobot ROS 2, Pick Place Demo, and let's create a new folder called Scripts. Okay, open that up. Copy these in. Okay, so we've got PointCloud.sh and robot.sh. So these scripts right here, they help you launch the necessary component for viewing point clouds and running the robot simulation with Gazebo, RViz, and MoveIt too. So this particular file right here, this PointCloud.sh, is designed to launch the robot in Gazebo and then view a specific point cloud file. In the robot.sh script, I'll open that now. This launches the full setup, the full enchilada, okay, including the robot in Gazebo, RViz for visualization, okay, and sets up MoveIt 2 for motion planning, the change. So yeah, that's it, just pretty much everything. So right now what we need to do is let's make all of these executable. Actually, let me have a look at that again, let's go into source, MyCobot, Pick Place Demo, scripts. Let's look at that robot.sh again. Okay, yeah, that's fine. Okay. All right. Now we need to make these scripts executable. Let's do cd ... scripts. We need to do change mod plus x PointCloud.sh, and let's do change mod plus x robot.sh. Okay. One launches the point cloud viewer, the other launches the actual robot. Let's add the RViz configuration file. Let's go back over here. ROS 2, source, MyCobot ROS 2, Pick Place Demo, and let's make a folder called RViz. Okay, and let's go inside here. New window. Let's go downloads, MyCobot ROS 2, Pick Place Demo. RViz. Let's copy that. Put that here. So we haven't built our package just yet using build, but it's helpful to know how to test the point count data in Gazebo once everything has been built. So to confirm the point count data is being generated successfully in Gazebo, you would run this command, bash ROS2 source mycobot ROS2 mycobot bring up scripts, and then mycobot Gazebo MoveIt.sh. Yeah, this one, Gazebo and MoveIt.sh. So you'd run this. Okay, and then you would go over here, open another terminal to go to ROS2 topic echo. Actually, let's do ROS2 topic list first and see what we got. Okay, we got this guy. Okay, these are our points and then our camera information. So let's just run this command to confirm data is being generated. So do ROS2 topic echo camera head depth camera info. Okay, we got the data coming out. That's good. And let's do ROS2 topic echo camera head depth color points. Okay, got our point cloud. Now to see the frequency of publishing, we would do this. ROS2 topic hertz, camera head, depth, camera info. Okay, you see we are publishing about 3.4 hertz, 3.4 times per second. And let's see how fast our point cloud data is coming. So ROS2 topic hertz, camera head, depth, color points. Let me just check that. 1.7 hertz, 2 hertz, 2 times a second. Not the fastest, but it'll work. It's not like things are moving in the environment. And now to get more information about the topics, we do ROS2 topic info, camera, head, color, image underscore raw. Okay, we've got one publisher, no subscribers, and let's do the same for the point cloud. Depth, color, points. Okay, our cloud of points showing the position and orientation of objects in the environment. So we got our point cloud. Okay. Let's go over here to RViz. I'm going to click on, let's go over here. Let's click that. Let's expand this out. Let's click the add button. For now, we're going to go over here to by topic, and I'm going to camera head, depth, color, and then points. Point cloud. Let's see if we can see the point cloud in here. Oh, that's a beautiful point cloud. Look at that puppy. Look at that puppy. Look how beautiful that point cloud is. We can see the cardboard box. We can see the Cheez-It box, our Coca-Cola can, and our mustard bottle, and our red cylinder right here. Looking good, looking good. Looking really nice. Let's go over here to gazebo, and it's pretty close. Okay, so this is reality over here in gazebo. And then we go over here and we can see our point cloud. We can also go to add by topic, camera head, color, image raw, and let's click image, see if we can see. Yep, got a nice little image over here in the bottom left you can see. Looking good. By the way, to see gazebo topics, so we use ROS2 topic list. If you want to ever see gazebo topics, you can do GZ is gazebo, and then topic, space, and then -L. Okay, so here we have all of the different topics, and you can see our point cloud right there as camera head points. And we are funneling that over to ROS2 using the ROS2 bridge, which we discussed in an earlier tutorial. And if you, let's just use this one, for example, camera head points. So I want to find out more information about that gazebo topic. We would do GZ topic, space, -T, and then camera head points, and then -I. And here we get information about the gazebo topic type right there. Let's close that. And yeah, let's go ahead and just press Ctrl+C to close everything down. In this section, we're going to create a ROS2 service that processes point cloud data to generate collision objects for a MoveIt planning scene. This service will segment the input point cloud, fit primitive shapes to the segments, like boxes and cylinders, and create corresponding collision objects. The service will also provide the necessary data for subsequent graphs generation should you decide to use a graphs generation strategy other than the one we will implement in this tutorial. Here's a description of the service on a high level. Okay, so we've got the input, the request. Okay, the request, the input is going to be the target object shape, either a cylinder or a box. You can see the objects in here. We can model them. We have got the cylinder here. We've got the Coke can. We've got the mustard bottle. We've got the Cheez-It box and the big box. So we're going to model those as a primitive shape, either a cylinder or a box. We're going to approximate, okay, the object dimensions, and that's for identification. And the output of our service, okay, the input is that. The output of our service will be a planning scene world, which will contain collision objects for all of the detected objects in the planning scene. Okay, the box, the cylinder, the Coke can, the mustard, the Cheez-It. It'll have a planning scene world in RViz, which will have all the collision objects, okay, which are the primitives, cylinders or boxes. We'll also spit out the full scene point cloud as well, an RGB image of the scene, and then the ID of the target object that we want to pick up. In this case, we want to pick up that red cylinder. So you get the ID of that, and then the support service, which is that gray part underneath all the objects. Okay, the ID of the support service, and then a Boolean success flag as well. That's how this service is going to work. So let's create a new package called MyCobot Interfaces to store our custom service definition. Okay, and this package will be used across our MyCobot projects for custom message and service definitions. So we're going to start in here in the ROS2 source, MyCobot ROS2. And let's create the new package. So I'm going to do ROS2 pkg create --build -type amend _CMake dependencies And we've got to add, let's add MoveIt messages, sensor messages, RCL CPP, license, BSD, 3 clause, -- maintainer name, Ubuntu, -- maintainer email, automatic Addison@todo.com, -- description, and then service definitions for generating MoveIt planning scenes from PointCloud data, including segmentation and primitive shape fitting for collision objects. Okay, and the name of the package is mycobot_interfaces. There we go. We created our package. Now let's navigate into it. Create a new folder called SRV, which will be the folder that will hold our service definitions. Okay, let's update the package.xml. All right, and let's go over here to our GitHub repo. Just copy the whole darn file. Okay, and let's put it over in here. Okay, got all of our stuff there. Let's update the CMakeLists.txt. Copy all that. Copy and paste in here. Okay. Let's just comment out some piece right now because we don't yet have the service set up. So let's just comment this lines out here. Comment that. So comment. Otherwise, this will try to bark at us when we try to build. So let's just save it. Okay, and then let's try to build. Let's open a new terminal. CD ROS2. :build. Packages. Select. mycobot_interfaces. Let's source the bash. All right. Now that we have our mycobot interfaces package set up, let's create the custom service interface for our planning scene generation service. So let's go over here to serve. It's this guy right here. And we need to go inside of our package. ROS2, source, mycobot ROS2, pick place demo. And let's go over here to where we go? Nope, we got to go actually to interfaces. Right there. Serve. And let's copy this file into the SRV folder. Right there. You can have a look if you want. Here's our definition. Okay, just as I said. The input is the target shape that we want to pick up. Okay, either a box or cylinder and the target dimensions. And the output is this. So let's close. And let's go over to CD source, CD mycobot ROS2. CD mycobot interfaces, SRV. Let's open, let's see, no, not there. We need to go to the CMake list so we can build this. Okay, and let's uncomment. There we go. So this is the meat. This service is the meat, my friends. This service is the meat. Input the target object shape, either cylinder or box. Okay, but in this case, we're targeting the cylinder. We're targeting the cylinder. That's what we want to pick up, that red cylinder you saw, and then the expected dimensions of the object that we want to pick. And we're going to response, that service is going to respond with all of this information. And then a success flag if we successfully picked the object. Okay, so that's there. Now let's go over to what do we need to do now? So we have uncommented the CMakeLists.txt. So next step is let's go over here to the workspace. And let's run a colcon. Let's clear that, run a colcon build. Packages, select my cobot underscore interfaces. Take a little longer, so now we have that service. Okay, and let's source the bash. Okay, now it's time to confirm the custom interface. So after creating that custom service interface, you always want to verify that it's been created correctly. And here's how you do that. So you're in your workspace and you're going to do ROS2. Okay, and let's do interface show my cobot, the name of the package, interfaces /srv/get planning scene. Okay, just like that. So ROS2 interface show my cobot interfaces srv get planning scene. And press enter. And here you can see the whole interface, the whole shebang, whole message definition right there. So remember, when you make changes to your interface, you need to rebuild your package again and source your workspace again for the changes to take place. So now you have created a custom service interface for planning scene generation, and this service will take a target shape and dimensions as input, and then it'll return a full planning scene world, a point cloud, the RGB image, target object ID, support surface ID like a table, and then a success flag that everything went well. Okay, so let's see what is next. So to use this service in other packages, you need to add the MyCobot interfaces as a dependency in the package.xml. Okay, of the MyCobot MTC. I'll show you that here. CD source, CD MyCobot ROS2, and let's do CD MyCobot MTC pick place demo. Okay, and let's go to package.xml. Okay, got this right here. And this is a my MTC pick place demo. So let's go ahead and let's just add this as a dependency. Okay, I'm going to my cobot underscore interfaces depend. So we need that. Okay, and okay, and if you ever wanted to use that in a piece of code, you would have to do the pound, this service, you do pound include, and then my cobot interfaces serve get planning scene.hpp, like that. And you'll see that header in some of my code in there. So once you have that, you can then create service clients or servers using that interface. So that's it right here for our custom service interface. Provides a clear contract for communication between your PointCloud processing node and other nodes in your system that need planning scene information. Okay, now it's time to edit the CMakeLists.txt. And to make it easy on ourselves, let's go over here to our package. Open up, get it, CMakeLists. Let's copy all of this stuff. Let's just make it easy on our lives. Copy this and paste. So here is the build file for all of our files. Okay, and we'll save. Okay, let's open this package.xml. And let's just copy the whole thing. Let's go over here to our workspace. Source, MyCobot ROS 2, pick place demo, and package.xml. Just copy the whole thing and put it in there. You can see we still have our MyCobot interfaces there as a dependency. So let's save. Save. Close that. Let's build the code now. We will do this in stages due to all the developer warnings you'll usually encounter when trying to build the MyCobot MTC pick place demo package. So first, let's go to the ROS 2 workspace. Do that now. Let's do colon build -- packages -skip. And for now, we're going to skip the MyCobot MTC pick place demo package. Good. Nice, nice, nice. Now let's source the bash RC. Okay. Now let's build the MyCobot MTC pick place demo package. By the way, if you don't do this W&O dev, you're going to get a warning and a whole bunch of stuff. So just do that. It's going to take some time. Let it do its thing. All right, now it looks like we've got some build errors, and I'm going to make this change in the GitHub so you won't have to face these demons right here. But let's go here, and we got mtcnode.cpp. So let's go have a look at that. Let's go to ROS 2. Let's go to source, MyCobot ROS 2, and mtc demos source. What's the file? Actually, no, it's pick place source. MTC node. Let's open that up. And where is it screaming? It's screaming on planning scene.h. It's saying to use .hpp instead. So let's go over here. Let's look for planning scene.h. Right here, we'll do .hpp. so that it's nice and happy. Save. And let's go down here. Planning scene interface.h. It wants us to do .hpp there. So let's do that. All right. And let's try the build again. First let's source bash rc. And let's try the build again. Okay, now we have built everything. Okay, let's just do a following command in here. And let's go here. I'll show you this massive command. Okay. I suggest pausing the video, taking a look at this command, okay, and typing it all out piece by piece. It's a monster. It is a monster. But this command will help you a lot because what it's going to do is it's going to silence a lot of warnings that you're going to get with the PointCloud library that will happen during the process of pick and place. So pause right here, type it. Okay, and then when you're done, press enter. Get the password. Okay. Now let's build one more time. Let's use the build command, full build command. A lot of packages, 69 different packages for ROS 2. It's a lot. You can see that everything has been built. Let's clear. And now it is time to launch everything. Okay, the moment you've been waiting for, it's time to launch the code. Before that, let's do aliases, some aliases here. That'll make it easier for us. We've got the PointCloud alias. So I've got echo, alias PointCloud, bash, blah, 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 PointCloud.sh. Okay, and just add that. And let's add another alias called pick. So you're going to type this command. So just briefly, let me just explain what's going to happen. When we launch the pick sequence, we're going to open the gripper, approach the target position, grasp the cylinder, execute the lifting motion. Then we're going to move to the target destination, lower the cylinder, release the gripper, and then retreat back to the home position. Okay, let's open a new terminal window. Let's run it, PICK, that runs it. Let everything come up. Looking good, my friends. You can see the MoveIt planning scene was generated. Looks just like our gazebo world. Pretty cool. See that? Here's our gazebo world right here, and here's the MoveIt planning scene. Okay, let's see if the log stopped. It did. Looking good. Now, the camera tilt angle does make a big difference in the quality of the MoveIt planning scene. You can experiment with different values by modifying your URDF of the Intel RealSense camera. So I'm going to click up here and pick and place task. Let's choose this. Choose that solution, which was the lowest cost solution. Okay, you saw the plan. Now let's attempt to execute. Click the execute button. Here's where we hope everything goes well. Alrighty, let's go over here. Completed trajectory execution with status succeeded. Hooray, that is exactly what we wanted. And you can see over here in Gazebo, that red cylinder, which was originally here, has been moved over here. Pick and place was a success. Right, now let's go over to the terminal. Let's do Control-C to close everything. And before we finish, I want to launch the PointCloud alias, and this allows you to visualize the raw 3D PointCloud data. Okay, let's do that. Let it come up. And here is a nice tool where you can visualize the raw 3D point cloud data in RViz. So that point cloud bash script enables you to visualize our beautiful point cloud with the Cheetah Cheez-It box, the Coca-Cola can, the mustard bottle, the red cylinder, and the cardboard box. By the way, when we launched the robot, remember when we launched the robot with the pick and place task, and if you have some issues when you attempt to execute the plan, your robot stalls as it tries to pick up this red cylinder, I recommend you go to your SDF file for the Gazebo world and experiment with different physics engine plugins. That's what I did to get it to work. So that's it for our full perception-based pick and place pipeline. On my website, I've got a lot more detail in the appendix for this tutorial on exactly the nuts and bolts and how all of these pieces of code in here, let's go here, all these different pieces of code work, what they do. I've got a reference as well to the academic paper that it was used to create the pipeline as the basis, the template for creating the pipeline. I took quite a bit of ideas from the paper and did some modifications as well. And yeah, I'll actually show it to you. I think it's worth showing it to you. Give credit to where credit is due. So I use this paper here as inspiration. I'll show you Goran, Lucian, let's see, depth cameras. Let's see if we can find it. Actually, let's do Google Scholar. This guy. Let's go to PDF. And it is not letting me get to it. Okay, let's click over here. So here is the website, and that's the PDF. And you might be able to, you can purchase it through here, through the IEEE to get the paper. But here's the abstract. But the name of the paper is called Robustly Segmenting Cylindrical and Box-like Objects in Cluttered Scenes Using Depth Cameras. So I used a lot of the ideas from this particular paper, okay? And I created scripts, my own custom scripts from the ideas in this paper. So in the big appendix for this tutorial on my website, you'll see exactly my step-by-step description and my explanation of all of the different pieces of code that are in here that make all of this work. It's actually quite complex to see an object, get its location, and then have the arm make the appropriate calculations to be able to pick it up and place it at a target location. I hope you have enjoyed this tutorial, this whole series on manipulation. I have enjoyed teaching this a lot. Thank you for watching, and as always, keep building.